Well, welcome everybody. I'm excited for us to kick off the P&C Design Challenge together. This is a 4-day live virtual training event via Zoom on protection and control design fundamentals. I'm Joshua Tim. I'm the founder and the principal of Power Transformations, and we train and mentor the P&C leaders of tomorrow. I'm coming to you live today from Charleston, South Carolina, my hometown, here in my studio. And I invite you all to participate right now as we kick this off by going to the Zoom chat window and typing in, where are you tuning in today live from? What city or state, country? I know we have some internationals in our audience as well. And as well as typing in, how many years of experience do you have in the protection and control field? Not total years of industry experience, but just P&C experience. Those two things, I'd love to get a feel for our audience and allow you all to get to know one another a little more as well. Thank you to those of you who have turned on your videos so far. I can see at least one of you. I'd love for you guys to participate in that way in this virtual learning environment. You know, this is the best kind of classroom experience we can have in such a distributed geography situation in the COVID pandemic days we're in. So I see a number of folks responding here on the Zoom. North Carolina, Michigan, Maryland, Texas, South Carolina, Pennsylvania, Indiana, Illinois, New Jersey, quite a few different states around the US on here. I know we have some from other countries as well. I'm trying to see if I can pick those out. But I'm seeing years of experience varying from 0 in some cases, and that's awesome. Junior engineers, 0, 1, 2 years experience, all the way up to some veterans with 10 or more years experience. We've especially developed these courses for junior engineers, younger, less experienced in our industry. These are fundamentals courses, but if you're a mid to senior level engineer, have no fear. I've had a lot of great feedback coming from those more experienced folks as well through these training experiences. So it's been exciting to see this movement growing, to see a growing community of passionate, creative, excellent protection and control engineers with released potential. And they're all across the industry from around the world, 25 plus countries now, as well as students from utilities and consulting firms across our industry. But we're all here devoted and dedicated to learning and developing in this specialized niche professional field, protection and control engineering within the power systems industry. So you're in good company, whether you're this is your very first challenge with us, or whether some of you are members that have been repeat students from a long time, over a year plus. We welcome you to this experience, which I believe is going to produce a transformational result, both in your minds, increasing in knowledge and understanding and competence, as well as in your hearts, increasing in confidence to practice this profession. You know, this is our 11th challenge now, our live virtual training event in the P&C Fundamentals training series of courses that I've developed. We started these about 1.5 years ago in mid-2020 timeframe, but this is our first live course of 2022. So I want to wish you all a happy new year. And I suspect that some of you perhaps have developed for yourselves a New Year's resolution that you want to devote more time, energy, and focus into growing and developing in your career as a protection and control engineer or technician. And if you've gone through that, perhaps you've looked back over 2021 and identified some technical gaps in your understanding. And from there, you've said, okay, what steps am I going to take in 2022 to help close those gaps, to pursue that learning experience? Well, I'm thankful you've chosen to join us today to be a part of that. If you haven't done that exercise yet, I'd encourage you to do that. It's a great transition of the year time to think back over your goals for the year ahead for 2022. I see someone from Ecuador on there. Welcome from around the world. I'm grateful that we're kicking off this new year together to work through this learning curve in the P&C field. It can be a steep learning curve at times. I'll share more with you towards the end of this training event later in the week about ways that you can partner with power transformations on an ongoing basis with our membership program. And that can give you a clear path forward for a longer term development plan if you need that help. But in this particular course, P&C Design Fundamentals, it's been my most popular topic yet. The most number of students enrolled. We have over 40 people on the live right now, and a number more that are registered watching the recordings. And so I believe it's because this is such an important topic to our P&C field. It's relevant whether you work in transmission, distribution, industrial, or generation P&C systems. It's relevant all of those areas. It's also a foundational concept, whether you work primarily in the P&C design area, whether you work in the relay settings and studies area, or whether you work in testing and commissioning realms. It's relevant to all of those areas within the P&C field. And if you're a college student, it's a great way to pursue getting a new career path within the protection and control field. Again, these are fundamentals level courses, so you're not going to be left behind. Most of my other courses have had a stronger emphasis on the different protective schemes and relay settings side of those schemes. So things like bus protection, transformer protection, transmission line and distribution feeder protection, and breaker failure and reclosing schemes, et cetera. Well, this topic of P&C design is relevant to all of those areas. It is quite applicable. So perhaps I maybe should have done this course earlier in my series, but I've had questions come in from students along the way. I remember one time I was teaching on bus protection schemes, and a student asked me when I was showing in a relay front panel view with test switches underneath the bus differential relay, and they're like, what is a test switch? I've never heard of that. I don't know what this means. I love those kind of questions. I really encourage my students to have a dynamic interactive Q&A experience in these live training challenges. So my request to you though is if you have a question at any point along the way, feel free to type it in the Zoom chat window at any time. And I will periodically pay attention to your questions as they come in and address those. But also I'll stop at various times throughout and open the floor. If you have a question, you can feel free to unmute yourself and ask that at those opportunities as well. Just like I love to see your faces on the videos. Thanks for those who are participating. I also love to hear your voices too. We are all people out there in this virtual world. You know, I found that a lot of times college and university programs, your coursework and experiences don't cover these concepts or principles. It's unfortunate, but perhaps it's just too practical of a topic. That's why I'm developed this course to, especially for those that are newer to the industry and missed out on learning this in an academic experience. So I'm going to show a screen share now of the topics that we'll be covering together in this course. Can you confirm, someone, that you can see my screen okay with the list of topics?
Yes.
All right, thank you, sir. So this is the topics we'll be covering in this course. You all saw this when you signed up and registered, but I want to point out a few things to you, kind of give you a feel for the flow of the week of the 4 days. We're going to start today with introductions and basics, and we're going to really be jumping down here to a lot of these common components that we see in protection and control systems, because I want you to all understand what these different components are, because then once we get into all these different types of P&C drawings, you'll be finding those components show up in them. So that's to leave nobody behind. Perhaps you've never been to a substation, never had a field visit, never gotten to set eyes on some of these things. I've got some pictures and some show and tell to show you along the way. So that's kind of how we're going to progress along. We'll probably spend a day on single and 3-line diagrams. We'll probably spend a day on DC and AC schematics, and maybe a day on relay panels and wiring diagrams for the subsequent few days of the week. These will be 60 to 90-minute sessions. So hopefully you blocked off on your calendars up to 90 minutes, but that allows us some time for Q&A as well. So that's where we're heading. But I want you to understand that with these different drawing types, in previous courses, I've maybe pulled up a relay settings software program and demonstrated to a real life case study of those fundamental concepts we learned in the settings realm applied to an actual relay manufacturer and model. Well, in this course, we're not going to be looking at relay settings software. Instead, we're going to be looking at these different drawings. And I'm going to start with some whiteboard sketches to give you the underlying concepts to help you grasp these different building blocks we use in these types of drawings. But then I'm going to also pull up a screen share of some actual real life substation P&C drawings packages and allow you to see them all together as well. So that's what you can expect for those case study demonstrations. Don't forget about the Q&A throughout. Take advantage of that on the Zoom chat window. So I think we're good on introductions here. I hope you have some pen and paper ready to take some notes. I do not believe in death by PowerPoint. That's just not my teaching style. That'll put you to sleep. Instead, I'm going to be doing those whiteboarding and screen sharing. It's going to be very interactive and dynamic throughout. But like I said, later on, we'll be pulling up those completed drawings and you'll get to see it all demonstrated together. But to start, we're going to break it down. We're going to allow you to focus in on some of these key crucial concepts, which will be guiding you later on as you develop a fuller, more complex drawing set. So we're going to dive in together to the P&C Design Challenge, starting with, what do we mean by P&C Design? Some of you may not understand that term and recognize or understand the implications of that. P&C Design is actually a defined skill set within the protection and control field. We're talking about developing the drawings package for a protection and control system, typically in maybe a transmission or distribution substation environment, maybe an industrial power system environment, a generation P&C system. This could be 20, 50, 100 drawings in a set. Maybe the 20 is closer to a smaller distribution substation environment. Maybe 100 sheets would be something more like a larger transmission P&C system. But we're not talking about in this course modeling the power system in a studies software for fault and coordination studies, things like Aspen, ETAP, CAPE, et cetera. We're not talking about calculating and developing relay settings, and we're not talking about testing and commissioning in the field of these relay systems. The P&C design part is the first step. It's typically done before you develop relay settings. Typically, it has to be before you construct it and before you go out to the field and test it and commission it at the tail end, the last phase of a project. So the P&C drawings package is that prerequisite, comes first. Typically, that settings engineer is going to use those drawings as they're developing the settings. And also the test and commissioning engineer or technician is going to be using that same drawing set as they verify in the field. Was it constructed per the design? If you're a recent college grad, you might not be aware of that nuance within the P&C field. There are these different sub-expertises that you can get engaged in. If you're lucky, perhaps your employer allows you the opportunity to get involved in all three of those areas: P&C design, settings, and testing. But oftentimes at the larger utilities and consulting firms, I find that they like to specialize or kind of box you into one of those three realms. And then you have to coordinate with others that are specialized in those other two realms. So keep that in mind if you're in the job searching phase as a junior engineer, to be aware of what types of opportunities are in this P&C area. In this course, we're going to get into the different types of P&C drawings, like I said, and the purpose of each of those drawing types. We're going to talk about the typical contents we find on each. We're going to look at some of the case study examples of each, but especially for those junior engineers out here in the student audience, We're going to start by introducing you now to giving you an understanding of the different components that make up this P&C system and showing you those on the drawing types later on. So let's start with my favorite place to go, a whiteboard sketch. We're going to go back to a screen share again. And we're going to go to Microsoft OneNote. And I'm going to begin doing a sketch. I encourage you, if you're taking notes, to draw it along. You know, I believe that the process of drawing it out on your paper actually helps you to engage more and learn it and remember it better. So I'm going to do a simple one-line diagram. This vertical line is a bus. This square is a circuit breaker. And then this is, let's call it a transmission line. This is a one-line diagram of the primary power system with a single bus, a single breaker type line bay architecture. So this is truly a three-phase power system, and we're going to see later on three-line drawings that we're going to break this out, phases A, B, and C. But for now, we're going to summarize it into a one-phase equivalent. And then I want to bring in a relay. I'm going to copy it over here from my earlier preparations and paste it in here to our sketch. And I just grabbed this off of a SEL website. It's an SEL 421 transmission line protection relay, commonly used for transmission line applications. And then what we're going to do is I'm going to show you these different components that make up the P&C system. Let's start with our CTs, our current transformers. Typically, a lot of times we'll pull those CTs from our circuit breaker bushing CTs. And so remember, the square is a circuit breaker. And I'm showing you that arrow to show you the flow of information here. So I'm going to write CB, that's for circuit breaker. This is our CT. I'm going to add another very important thing to our CT, though, that we'll talk about a good bit in this course. And that is polarity dots on the primary side and on the secondary side. We'll get into what those polarity dots mean later on, but that's important. Anytime you're drawing CTs on a one line or a three line on an AC elementary, you want to be aware of your polarity dots. Another thing that transmission line relays typically need, we covered this pretty extensively in some of my previous courses, the distance and directional challenge, the pilot protection challenge, for example. But we also oftentimes have PTs wired to our transmission line relays. Let's go with purple. Yes, I'm a Clemson University alumni, orange and purple, go Tigers. I don't know, we got any other Clemson Tigers out there? Type it in the Zoom chat. But this is going to be our PTs, okay? This is not a power transformer. This is a potential transformer, sometimes also called a VT, a voltage transformer, where it's bringing in a measurement of the voltage. Again, this is a one-line equivalent. There would really be three PTs and three CTs in this set. So these are the inputs coming into the relay as far as AC inputs. You know, sometimes I've drawn this as a line side PT. I'm talking about this is the line side over here. This is the bus side. And so over here, we've got sometimes these PTs, these voltage signals come from bus PTs instead of line PTs. But this is probably the more preferred approach if you have them line PTs available. Note that another term you might use is that these are bus side bushing CTs on this circuit breaker, because they're on the side of the bus closest to the bus rather than the line. But we're using it for line protection. We'll draw that out later to help you understand. So we bring in these currents and these voltages to our relay, our protective relay, and then the relay processes those and determines whether there's something wrong, whether there's a fault, an abnormal condition on the power system. It makes a decision. If this is a fault, it needs to take automated action to clear or isolate that fault. And so it's going to send some signals out from the relay to the circuit breaker. And we're going to draw those here. I'm going to use green for trip, That's a pretty common industry color that we use for such things as tripping. And we usually use red for closing. This would be for like an automatic reclosing type signal, perhaps. So green is T for trip. And then the red over here is C for close. A lot of times at higher voltages, our breakers have more than one trip coil. We might have a trip coil 1 and 2 used for like a primary and a backup relay. It gives us a level of redundancy in case one of those trip coils were to burn up or go bad and not function, that we could hopefully count on the other trip coil to operate. This is showing just a single relay. A lot of times we have primary and backup relays as well. But this is about as simple as I can make it from a high level perspective, the essence of what you should expect from a protection system. CTs and PTs coming into your relay, trip and close signals coming out of your relay. There's usually other DC type signals coming in and out of our relay as well. Sometimes we choose to put those on a one line, other times we don't. We'll go into that more tomorrow. But this is kind of the bare bones, okay, that you should expect to see on a one line. This is kind of a sneak peek to what we're going to begin to see on those types of drawings. You should expect to see the primary power system with its layout, its architecture of buses, lines, transformers, both transmission and distribution lines if it's a T to D substation. You should expect to see circuit breakers and other switches, maybe a manual gang operated disconnect switch or a motor operated disconnect switch. You should expect to see your CTs and where they're located and what their polarity dots are and which CTs are wired to which relays. You should expect to see your PTs and where they're connected to the power system on the primary side and which relays they're wired to. And you should expect to see trip and close signals going from your various relays to your various breakers on the system. Now, this is very simple. One bus, one line, one breaker. It's going to grow quite a bit as we get a whole substation, but this is giving you the essence, helping you grasp the concept. So now that we have this higher level perspective, let's look at each of these components individually. But before I go there, are there any questions so far at this high level? I see someone else as a tiger, but it looks like it's a different type of tiger. RIT tiger, you'll have to explain what RIT is to me. Maybe another university, perhaps. Oh, North NC State Wolfpack, that's another out there. Okay, gotcha. Rochester Institute of Technology, okay, thank you, welcome. So we're going to start diving deeper here on the relay side. And I'm going to start here because this is kind of the brains of the whole show. It's what's running the show. It's what's making those decisions and taking those actions, driving those actions to be taken on the power system. So what is a protective relay? I think most of y'all are familiar with this. I'm going to give a very brief summary for those that are not. Essentially, it's a computer. Nowadays, it's a microprocessor machine, and it's monitoring the power system from the voltages and or current signals and other input signals to detect anomalies, abnormal conditions, faults. And once it determines that fault exists, it's going to take an action to automatically drive a response to clear that fault, to isolate the faulted section of the power system. That relay is going to command one or more circuit breakers to open, to trip. And then once that is open circuited, then the faulted section of the power grid is de-energized, is in an outage condition, and it's been protected from further damage at that point, protected from damage to human life and perhaps a risk of fire or explosion, et cetera, fault current conditions. We used to use electromechanical relays in earlier generations with moving parts and discs and coiled springs, et cetera, we're not going to really get into those in this course. We're going to focus on the modern day state of the art with microprocessor relays. Nowadays, you use a computer program to send settings to a microprocessor relay. Again, we're not covering the settings side here in this course, but I know of a lot of P&C design engineers who are very familiar with how to do all the designs, but what goes on inside the relay box is kind of this nebulous mystery. It's like a black box. If that's you, I encourage you to check out some of my previous courses where we go into those details of the different protective elements, the setting side, what goes inside the box. But in this course, we're focusing on the inputs and the outputs from this relay. I see a question or maybe a comment. I guess I'll address that in my next stop. 421 is what I kind of grabbed here as a drag and drop for this diagram's sake, but I want to give you a little more zoomed in view of the front of a relay. This is one particular manufacturer and model. The front of the relay, push buttons for the operator to control different things, some target LEDs and displays to show the operator different information and statuses and alarm conditions, etc. But note that this relay has these mounting sides where you can put a screw in and actually put this relay into a relay panel. Some of you may or may not be aware of where these relays go in the protection system. If that's you, I've got an image picture that will kind of give you some more visual understanding of that. This is a relay panel lineup in a substation control house. This happens to be a distribution substation, a somewhat smaller lineup, but in each of these, we've got a number of relays in a panel. We've got test switches, which we're going to talk about in this course. We've got some lockout relays, which we're going to talk about. We've got some control switches, etc. All of this is mounted inside of this relay panel inside our house. On the back side of a relay panel, it looks a little bit like this. You've got the relays in here with a bunch of terminal blocks. We're going to talk about those in this course, and some fuses. We're going to talk about those. You've got the back of the relay here and the back of a lockout relay, which we're going to cover. All of this is just giving you the broad perspective right now. But sometimes we don't have the relays in a control house. Sometimes for a smaller substation, they actually mount the relays inside of the circuit breaker control cabinets. And so this would be an example of that. This is a circuit breaker, and inside the breaker is the protective relay mounted in there. It's also got a test switch, control switch, selector switch. We're going to talk about all of these in this design course. So that kind of gives you a perspective of where these relays end up. But that's kind of a front view. We're not going to focus much on the front in this course, though. Most of our focus is going to be on the back of the relay. And this here is again, an SEO 421 rear view. We covered this, used the same relay in some previous courses as a case study demonstration. So I'm just kind of sticking with that theme for those of you that are repeat students. Anthony pointed out that these look familiar. So I'm glad you're picking up on some repeat content here. You know, sometimes these relays are also mounted in like a NEMO weatherproof enclosure cabinet out in the substation yard if you don't have a control house. That's another option as well for where these relays are mounted. So on the rear view, we have a whole bunch of screws for terminating wires to. These are wire terminals. What do we mean by terminal or termination, terminating? That's the end of something. You know, if your employment is terminated, you're fired, right? That's the end of your employment. Well, this is where we put the end of our wires. We land them or attach them and connect them to these different screw terminals. I want to point out a few things to you on the back of this particular relay. This is just one manufacturer and model, but a lot of these concepts are going to be relevant regardless of what relay and make and model you're using. So first, we've got a number of inputs and output contacts. And I'm not going to delve into those right now. I'm going to save that for when we get into more of the DC schematics discussion. But we've got a 100, 200, and 300 board for inputs and outputs. Quite a few I/O is how we shorten that a lot of times. Each input oftentimes has two contacts, each output two. There are exceptions to that. We'll talk about form A, B, and C contacts. We'll talk about these common shared input contacts when we get to the DC topic. But what I really want to focus in more today in this first session is the AC side of things, the currents, the voltages, because that's a lot of what we tend to show more on a 1-line and a 3-line diagram that we're going to go to next in tomorrow's session. And so I want to point out a few things to you. For starters, you see how there's actually two current inputs here on this transmission line relay. There's the W current terminals and the X current terminals. Why do we have two? I drew up this 1 line with a single bus, a single breaker, a single set of 3 CTs, A, B, and C. You could easily wire that CT to this W current terminal and you'd be fine. That'd be sufficient. But there's other situations on the transmission system, usually, not so often the distribution system, where we have 2 breakers at a line terminal. I'll give you a quick whiteboard sketch of that in case you're not familiar with this. Perhaps you have a double bus, double breaker kind of architecture. Maybe I should specify that horizontal line this time is the bus 1 and bus 2. And then I've got these squares, breaker 1 and breaker 2. And then I'm going to have a transmission line terminated here between these 2 breakers going out to another substation. But what about the CTs in this case where we've got 2 breakers? I would have CTs on that breaker bushing and CTs on this breaker bushing. So now I've got 2 sets of 3-phase CTs. And then I'd put the relay in here. Let's copy this down. Oh, undo. There we go. That's good enough. And so we bring in our CTs separately to this W and to this X current terminal on the back of the relay. We call that W and X. So hopefully you can see that. That's a double bus, double breaker. The same would be true if you had a breaker and a half with 3 breakers in the line bay. The same would be true if you had a ring bus, which has 2 breakers on a line. I see a follow-up question, explain the difference between double bus and breaker and a half. That's a great question. I think that's Hamad. So this is double bus, double breaker. I'm going to show you another case actually with a breaker and a half then, since you asked that, just so nobody's confused by this concept. We'll have still have 2 buses in the case of a breaker and a half, but we're going to have 3 breakers in our line bay. We're going to have 2 lines in our bay. And in the case of a line relay here, I'm going to just draw this relay this time. Let's actually say this is not a 421. I'm going to change it up on you. What if it's an older SEL 321? Well, we're still going to have 2 different sets of CTs coming here from line breaker 1 and line breaker 2. But if you've been around for a while and you understand some of these different legacy older era models, I'm going to pull up the back of a 321. I can find my diagram here, rear view. The back of a 321, I've only got 1 set of CTs that I can wire to. I don't have 2. So how am I going to handle that in a breaker and a half or a double bus, double breaker, or a ring bus application? I'm going to have to combine those 2 CTs external to the relay to parallel them to one another, and then wire in the combined line current quantity rather than the two separate breaker current quantities. So in that case, I would sum them up, parallel them external, and wire it in once to the current terminals. To answer your question, Hamad, breaker and a half, 3 breakers divided by 2 lines in the bay, 3/2, 1.5 breaker and a half terminology. So you can actually have 2 lines with 3 breakers rather than 2 lines needing 4 breakers if you needed a double bus, double breaker architecture. Great point there, Sean, about CTs. You're reading my mind on where I was going with that. I was going to say there are some advantages to bringing them in separately, like the 421 allows. And some of those advantages, like Sean pointed out, these could be separate CT ratios, and the relay can calculate and normalize the two to one another with math equations, versus when they're summed together external to the relay. This is how it was done in the electromechanical days as well. The CT ratios must match. We're going to go into more on what is a CT ratio if you don't follow that discussion. But then other added value capabilities of doing them separately. Now you can do like a breaker failure scheme in your line relay where you can get the separate breaker currents and determine if one or the other breaker fails and take action. You can do independent automatic reclosing schemes on these 2 breakers. We're not going into all those schemes. I've already covered those in previous courses if you're more interested in those topics, but those are some additional advantages of separating the currents into your line relay. One other advantage is you have less risk of CT saturation occurring. Again, beyond the course of this topic of P&C design, but maybe I'll teach a future course on CT deep dive, including saturation. But there's a good paper if you want to know more about this concept of paralleling CTs external to line relays, paralleling CTs for, this happens to describe line current diff schemes, but it also applies to any transmission line type application, whether you should parallel them external, whether you should bring them in individually or separate or combined. I do periodically point you to papers, tech paper references that I recommend if you want to do deeper dives beyond just a high level coverage of these concepts. So I'll upload those recommended tech papers to the course website at the end of the day when I upload the recording, and you can find your way there if you want to go further in your homework, completely optional. So I forgot to add one thing to these drawings though. Never forget to include your polarity dots, primary and secondary polarity dots, primary and secondary. The same would be true down here. Always a good idea to include your polarity dots on your drawings, primary, secondary, secondary. So we're going to look at that, but what do we mean by polarity dots? The convention of the industry is that current into the primary polarity dot equals current out of the secondary polarity dot. I'm going to go back up to my simplified drawing up here for this. If I have fault current flowing in to my transmission line, oops, I'm going to make that a little smaller. Excuse me. Let's go with that. Fault current flowing into my primary polarity dot, that's going to equal current flowing out of my secondary polarity dot. And the same is true, the inverse, the reciprocal of that. If you have current flowing out of your primary polarity dot, it's going to equal current flowing in to your secondary polarity dot. So that's kind of the convention, the norm. That's what we expect to see with polarity on CTs. The non-polarity side oftentimes gets tied together on the relay end. And I'll tell you what, I'll do a sketch of this to help. This is kind of skipping ahead to like a 3-line concept, but let's go ahead and do that now. help you understand that a little better. I'm going to take our 421 back and I'm going to snip it here so that we've got our current terminals. And then let's paste that in here. Gotta figure out the one node interface 1 second. There we go. And now let's draw our primary system, our one line once more, our bus, our breaker, and our line. We're just going to do a single breaker for simplifying this concept here. How would we wire? Actually, you know what? I meant to do a 3-line here. Let's try that again. Let's do 3 phases this time, okay? A, B, and C. And let's do our circuit breaker a little larger this time. And A, B, and C coming out of the breaker. In a circuit breaker, we typically have 6 bushings, 1, 3, 5, and 2, 4, 6. I'll draw that up in a little while, a little more detail. But let's draw our CT here. This is on the A phase. We're going to come into the A phase polarity dot. Let's note that the primary polarity dot, secondary polarity dot. So what happens is you wire the secondary polarity dot of your CT to the polarity dot on the back of your relay. And that's going to give you proper orientation so that current into your line zone of protection equals current into your line relay in the positive direction here. And you would see the same thing when we go to CT number 2 and 3, or B phase will come here, C phase will come here to that polarity dot. Again, we should always draw our polarity dots. I'm reinforcing and saying this over and over again because when you go to do these in CAD, you want to make sure that all these polarity dots are properly drawn. And then what about the non-polarity dots on the neutral side of these 3 CTs? What about the non-polarity dots on the neutral side of these relay current inputs? We typically will tie those together or jumper them together. Green is a common color for neutral. See, this is like a jumper. And then likewise over here in the breaker CT terminal blocks, we would tie those together and jumper them. And then we got to tie those 2 ends together from the breaker bushing CTs to the relay CT terminals. So we're going to bring that neutral over here. So what am I showing you here? This is more like a 3-line rendition of the currents and the CT circuits. What I can help you understand here is that typically this is 1 cable. This might be like a 4-conductor number 10 or a 10 American wire gauge is pretty common wire size that we use for CT circuits in a substation environment. So all 4 of these wires, A, B, and C, and neutral, are bundled together in that common cable jacket. And that's how we would go about wiring these current inputs on the back. Now, in reality, we're going to add more to this equation shortly. We're going to start talking about test switches and terminal blocks. In reality, we don't wire the back of the terminals of the CT directly to the terminals of the relay. There's more in the middle. Somebody's pointing out a good point. Where do we ground the CTs? You're absolutely right. I was going to cover that later, but since you asked, I will throw that in here now. We're going to ground it on the neutral part, but a critical part with CT wiring is that you ground it in one and only one spot. You don't want to have multiple grounds on your CT neutrals. So some companies' practices is to ground it in the back of the relay panel. Let's go ahead and draw that here. There's the ground in the back of the relay panel. Others may choose to ground it at the back of the, in the circuit breaker cabinet where this common neutral is instead. Do not do it in both, do it in one or the other. But one and only one spot is an important concept for CT circuit grounds. Great point for bringing that up. Reading my mind of where I was heading down the road. So I want to point out one other thing about these neutrals though. Notice over here on our one lines, I did not draw the neutral wire on the CT. And that was intentional. We typically do not include the neutrals on a one line. It just starts to get too cluttered and too many lines to keep track of. You know, this is simple, but when you start to get to 10 or more breakers and relays in the equation, you got lots of lines going around. So we typically just leave off the neutral from the one line drawing, but we will show it on the 3-line drawing. We're going to look at actual examples of these tomorrow, but hopefully you're grasping these concepts today. What about if you have multiple relays that need the same CTs to be shared? I'm going to do a one-line rendition of this for keeping it simpler. But sometimes you have a breaker and a relay. Let's draw 2 relays this time though. Relay 1 and relay 2. And suppose you did not have 2 sets of CTs, so you could do one set of CTs to one relay and the other set of CTs to the other relay. Suppose you only had one CT available. You needed to share that CT set for both of these relays. In that case, you would have your CT here coming into relay 1. It would come out of relay 1 and go to relay 2. And then from relay 2, I'm going to go to my green color for neutral. You would tie them together and you would have a neutral coming back around here on relay 2. So you'd have 3 wires coming into relay 1, 3 wires coming out going to relay 2. And then on the non-polarity dots of relay 2, you would jumper them together to make a neutral common and bring that return path back to the neutral of your CT. Again, always remember your CT polarity dots. And this is the polarity dot side and polarity dot side on the relay as well. So that is called sharing a CT. These 2 relays are in series with one another on the CT secondary circuit. That is another possibility, and we'll show you something like that on a actual 1-line and 3-line drawing later on. I've got a couple more points for CTs, but I do see some questions coming in. Before I get too far behind on them, let me pop back. I mentioned this is from Sintayehu. As you mentioned, taking VT from bushings and or from the line, almost identical. So I guess you're pointing out that whether you use line side PTs or bus side PTs from a protective distance element, for example, it will work either way. There's some pros and cons to that. You know, if the breaker is open, you don't have a true picture of what your line voltages are. And then I think I answered Hamad's question. Answered Sean's point. Grounding, we covered that. Why do we ground cable shields and what is the purpose of them? Ooh. Let's save that one for when we get into wiring diagrams in a later day. Y'all feel free to engage with one another on the chat too, by the way. If I can't keep up with you, I like to see that kind of community interaction along the way. But re-ask that question when we're talking about wiring diagrams later on. Let's stay focused on CTs for now, PTs on our analogs. So we're looking at the back side of the relay things. That's what we've been kind of diving into here. But next I want to take you to the other end of things. What about on the CT terminals themselves? You know, we looked at these current terminals on the back of our relay. But where are these CTs coming from? We talked about breaker bushing CTs. This would be a dead tank circuit breaker that has bushing CTs. If it's a live tank circuit breaker, it would not have those. You'd have to have a standalone CT stand, but that's usually much higher transmission voltage classes. Typically, we have breaker bushing CTs. And so let's look at the other end of things. I'm going to draw up a breaker for you. I told you I'd go a little further into the breaker bushings. Circuit breaker with phase A, B, C, in and out. So this is our circuit breaker. This is going to be bushing 1, 3, and 5 on the one side. And it's going to be 2, 4, and 6 on the other side. So 1, 3, and 5 would be coming in source side if that was the bus side, and then 2, 4, 6 would be going out load side, line side, if this was like a transmission circuit breaker. So always remember 1, 3, 5 side of the breaker or 2, 4, 6 side of the breaker. It's not 1, 2, 3, and 4, 5, 6. It's 1, 3, 5, 2, 4, 6. And what about the CTs on these breaker bushing CTs? We oftentimes will have CTs on both bushings or both sides of the breaker. What about the polarity dots? There's a convention to this. The primary polarity dot on the outside of the bushing, and then the secondary. Primary, secondary, primary, secondary. But on the other side of the breaker, your primary polarity dots, again, are going to be on the outside of the bushing, which is the opposite direction from the flip side. Why do we do that? Because if you had, say, a bus over here, you're going to be using these 3 CTs for your line protection, for your line relay. You're going to use these 3 CTs on the other side of the breaker for your bus protection, for your bus relaying purposes. And what you're going to see is this overlapping zone of protection. Just to kind of give you the concept, I might remove these lines later, but your line protection is going to be protecting that direction on the power system, right? These are lines continuing on, but then from the bus protection side, that's going to be different. That's going to be like this. Notice how the line and the bus protections, they overlap. We call that overlapping zones of protection. But essentially the polarity dots coming on this side are into the line zone of protection, the way we drew this. Here the polarity dots are into the bus zone of protection. So that's the reason that breaker manufacturers will standardize on sending you the breaker bushing CTs with that reverse polarity dot notation like that. I'm going to remove those zone of protection lines to be able to not clutter it up too much as I add another thing to this drawing, but hopefully that gave you that concept there. So again, I would call this the bus side CTs. This is the line side CTs. And we're using bus side CTs to protect the line, and we're using line side CTs to protect the bus. Keep that flip terminology in mind. And then another thing we sometimes see is double sets of CTs on either bushing. You can, when you're speccing out your breaker, if you have a need for a primary and a backup line relay and a primary and a backup bus relay, then you would have a desire for 2 sets of CTs on either bushing. So this is a total of 6 bushings, right? And then this is 2 bushing CTs per bushing. So we're talking about 12 CTs here on this breaker. When we have this situation, we usually call the outermost the X bushing CT, and the innermost we call the Y bushing CT. Here on the other side, the outermost is the X, and the innermost is the Y. So we've got the 1X, the 3X, the 5X, the 1X, the 1Y, 3Y, and 5Y CT. Same for the 246 side. Now, in case anybody's been confused by this, I have some pictures to show you, which might give a little more appreciation to what's going on here. This is an older breaker, 1980s style, and I think an old Westinghouse breaker. And you can actually see up here on these breaker bushings, here's the bushing CTs. You can actually zoom in here, and here's a bushing CT from that same breaker. You see on the nameplate, bushing current transformer. Looks like it's a 1200:5 CT ratio here. It also has a notation about polarity indication, the polarity dot being the outer side of the bushing, like we were just sketching up there. Inside the breaker cabinet, a lot of times we have a nameplate that shows the different CT taps. This is a multi-ratio CT, and so we can actually tap it down to a smaller ratio if we need to for a particular application. It's desirable, if at all possible, to keep them at full tap for makes you less likely that you're going to saturate your CT, but sometimes you don't have an option. You have to tap it down. You have to make sure you derate that CT if that's your situation. Again, kind of beyond this course, but just making you aware that with multi-ratio CTs, we have multiple taps. So if we wanted to do a 600:5 CT ratio, we would do the X2 to X4 taps. We would actually wire from the X2 to the X4, and that would be a 600:5 CT ratio, versus if we went X1 to X5, that's full tap, that's a 1200:5 CT ratio. So we'll look a little more at that later, but here's some pictures of those actual CT terminal blocks in this old breaker. This is the 1 and 2 bushings. There's the 5 taps brought in, X1 to X5. And notice it's 2 to 4. So this is a 600:5 ratio for this particular relaying application. Same with 3, 4, 5, and 6 bushing CT terminal blocks. And if we look at a little more modern breaker, did I hear somebody had a question or comment there? I will stop in just a moment to open the floor to questions, actually. This is an ABB RMAG. You notice here you don't see bushing CTs up here. They're actually buried inside of this high voltage compartment in the enclosure cabinet. But there are bushing CTs in here, even though you don't see them as explicitly. And if you look down in your breaker cabinet, you'll see these different bushing CT terminal blocks. You'll see the bushing CT nameplates, again, the 1200:5 at full tap. So you'll see the 135 and the 246 bushing CTs. This breaker has 1 CT per bushing, and looks like full tap X1 to X5 on the 135 side, but it looks like tapped down to X2 to X4 on the other bushing. That was a bus differential relay application that had to work with some old electromechanical relays. Let's see. I'm going to show you a couple more pictures, and then let's open to some questions. This is a higher voltage breaker, like 115 kV perhaps. You kind of notice subtly this little line between here. This is 2 different CTs on each bushing. So in this case, you've got 6 bushings, 12 CTs on that breaker. If you go inside the breaker cabinet, you'll see 3 times 4, 12 bushing CT terminal blocks for those different relaying needs and applications. That's the other end. That's the CT side that we're pulling from to bring into our relay current terminals. But sometimes you'll use transformer bushing CTs. I don't have pictures of that, but usually those transformer bushing CTs, you also won't see them out on the bushings. They're usually buried down inside of the transformer tank. But if you were to go inside of the transformer control cabinet, you should see something somewhat similar to this idea of a whole bunch of transformer bushing CT current terminal blocks to work with. So I'm going to look back at some questions before I proceed. Looks like y'all have engaged a little bit. Well, I haven't paid attention, so thank you for that. What's the benefit of having two CTs in the same side of the circuit breaker since they're connected in series to each other? In that case, they're not in series. They're kept as two separate circuits. I think this here, I should maybe clarify what we would do here. We'd have two separate relays. We'd have a primary relay and we'd have a backup relay. And let me label these: primary relay, backup relay. And so it's going to get a little cluttered here. I'm just going to do one phase, okay? Usually we do our primary on the outer X, and then our backup on our inner Y bushing CT. And so these actually are not going to be in series with one another. They're going to be going to separate relays to provide a level of redundancy. I think Sean jumped in there and answered that, so thank you for participating. And then I have a question from Hamad. Can you show examples of dead tank and live tank CTs? I do not have anything prepared on that as far as pictures. I'd have to Google search to find you some. I very rarely encounter live tank circuit breakers and live tank CT stands. That's maybe a 500 kV class at times. I've seen it out there on some of my client systems, but typically we're dealing with dead tank most often. Looks like Kevin also jumped in there to answer Cintayehu's question. So thank you all for participating, but hopefully this diagram cleared up that confusion there. Any other questions about CTs before I talk about PTs for a while?
Hey, Josh, Sean, was looking back at the pictures you're showing. Wanted to see if you could explain what that middle on the CT terminal blocks, what that middle strip on the terminal blocks were.
So we go here. This right here you're talking about, right? The shorting?
Yeah.
You're somewhat jumping ahead. I will talk about
that's fine. I figured.
But that is a shorting terminal block. And we're going to get into the different types of terminal blocks, including shorting terminal blocks. But you'll see these little screws here that you can short out your CT with. So stay tuned for the full answer to that. Great job thinking ahead there. Any other questions on, let's see, William asked a question. Do we ground the CT so they can be bypassed or shunted later using the test switches? You're correct. Kind of to that very shorting concept that I was just talking about with Sean. We're going to look at test switches and we're going to look at shorting test switches and shorting terminal blocks. And, if you're not using a CT, you should always come here and short them out in the breaker cabinet. If you're not wiring it to anywhere, you should have the full tap shorted out, either with shorting screws or maybe even with a jumper to do so. And the reason for that is you never want to have an open circuited CT. I do plan to talk about that later on a little more, but that's a dangerous, hazardous condition. You can actually build up quite high voltage, which is a personnel hazard. It can even cause damage to your CT, perhaps, if you have an energized primary system and an open circuited CT secondary system. And so you will commonly find different approaches that we short out the CT secondaries at times. We'll look at that with test switches and terminal blocks later on. What's the procedure to short the block? Good question. You'll take the screws and you'll put one on X1 tap and you'll put another screw on X5 tap. And at that point, you've shorted out the entire length of the secondary winding. You want to make sure that you do have a path to ground in there as well, I believe, from one of those three. Typically, the neutrals are jumpered together and then they go down to the ground. But the key thing is X1 to X5 full tap is where you want to put those shorting screws to make sure that you're not having any open circuit condition. Great point. You can see arcs as well. Not something you want to see. Well, great questions, great participation there. Let's move on to PTs, VTs, potential transformers or voltage transformers. I will open the floor later on for other questions if you have any other follow-up on anything we covered today. But, even at higher transmission voltage classes, we have CCVTs, capacitor coupled voltage transformers. But I've got some pictures for you. We looked at the back of the relay up here. We showed, okay, we're going to wire the PTs in. We showed the back of the relay of a 421. We've got these two different voltage terminals, similar to how we had two current terminals. Why two sets? You might have three-phase line PTs, and then maybe you have bus PTs as well. Maybe you have a double bus, double breaker situation, or a breaker and a half, or a ring bus where you need some sync check voltage sources. We talked about that in the auto reclosing challenge, if you want to learn more about sync check. But there are applications where you need more than just a single three-phase PT set wired into the back of your relay. Sync volt check, I should say. But this is the relay side of things, very similar to what we drew up on the CTs. You want the PT secondary polarity dot to be wired to the relay voltage polarity dot, just like we drew up on the CTs. That's kind of our conventional norm. But from a picture perspective, let me pull up a PT in the field. I can find my PT. For some reason, I'm not seeing the pictures there. Where did it go? Excuse me. CTs. There we go. PT primary. Sorry about that. This is a distribution class. This is a transformer coming off to a low side bus. And so this is effectively like a bus PTs. And so we've got the primary system coming down here through the fuse, coming over to one bushing of the PT, and then the other bushing is neutral, which is grounded. So that's measuring the phase to neutral voltage across this PT. There's three of these, one per phase. And then we bring this down through these conduits, these secondary wires. We bring it into a PT junction box at the base of the pole. I got a picture for you of that as well. This is one example of a PT junction box. You've got coming in phase A, B, C from those three primary PTs up top. And then from there, you can kind of jumper it down. These are fuses that you see here. And this is now taking A, B, and C phases, A, B, and C, A, B, and C, to multiple relays that need to share the same potential voltage signal. Down here, we've got a common neutral bus. All of these are jumpered together on the neutrals. So this is kind of a little example of a PT junction box. It's a common approach that companies take in their P&C design with potential transformers. We do have fuses on the PTs. Why is that? We didn't see those on the CTs. We have fuses because I guess I should ask you the question. Let me open the floor to somebody. Why do we have fuses on our PT secondary circuits? What are we protecting against? Any takers? Unmute yourself, type it in the Zoom chat. Why do we use fuses in general, right? Not just on PT circuits. We're protecting against, well, yes, protection. What type of fault condition are we protecting against on our PT secondary circuits? Over voltages, good guess. It's actually more of the other side of things. It's more of the overcurrent situation. It's short circuits. There we go. That's what I'm looking for. Good job, Kevin. So if you have a short circuit where the phase to the neutral gets shorted together, somewhere down line of those fuses, again, you could have an arc, you could have a high current situation. You want this fuse to open circuit to clear that short circuit fault on the secondary system. So we have these PTs, fuses to protect against short circuits. An open circuited PT is fine. That doesn't cause any harm. You got a potential difference you can measure across it with your voltmeter, just fine. But a short circuited PT is not a good thing to have. And so we use fuses to protect that. But on the CTs, it was the other story. We didn't have fuses. Why didn't we use fuses on the CT secondary circuits? It's because actually we're going to intentionally short circuit our CT secondaries at times with our shorting test switches, shorting terminal blocks, et cetera. What we don't want on the CTs is an open circuit. So exactly, to not create open secondary on the CTs. You know, how does a fuse blow? When it blows open circuited. So if we used fuses on our CT secondaries, we would have dangerous open circuit voltage buildup, arcs, damaging CTs, et cetera. So don't use fuses on your CT circuits. But we've got PTs with fuses in our junction box. But then let's look at one other concept with PTs. You remember on the CTs, we looked at the multi-ratio bushing CTs, the 1200 to 5 that could be tapped down, for example. Likewise with PTs, we oftentimes have multiple taps on the PT secondary system. And common voltages that you'll see for PT secondaries. Let's see here. PT secondary. I do have a drawing of this I'm going to pull up so you can visualize this a little bit. 67 volts is pretty common. We see 115 volts is pretty common that we see for taps. So in that case, you have a PT primary winding and then you have a PT secondary winding. And if you go full tap, it's going to be the full 115 volts, but you can also choose to go with a mid tap at the 67 volt range. One potential for confusion though, is that when you have multiple taps on your PT secondaries, you also have multiple PT ratios. And how do you know which PT ratio goes to which tap? I remember this from an old protection mentor of mine years ago. The smaller PT tap is the higher PT ratio, and vice versa. The higher PT tap is the smaller PT ratio. Why is that? If you go back to your basic fundamental principles, a potential transformer is nothing more than a transformer with turns ratio, right? And your turns ratio, you have N1 over N2, primary over divided by secondary. That's the number of turns in the primary winding divided by the number of turns in the secondary winding. So if we go with less than full tap, that means N2 turns is going down. The number in the denominator is going down. That means the overall turns ratio is going up. So that's why that's a good rule of thumb to remember. Let's actually look at a real life PT here in a one line drawing. This is the primary side. This is the secondary side. And you notice there's a 67 volt tap and 115 volt tap. And it shows two different PT ratios or VT ratios here. which ratio goes to which? Somebody tell me the 67 volt tap, which PT ratio should we use for that case?
1000 goes to 67, and then 600 goes to the other one.
The 115, exactly. Good job, Hussein. So smaller tap, larger PT ratio. Larger tap, smaller PT ratio. How would be a way you could gut check that if this is a 115 kV line? This is a good PT exam, PE exam question for junior engineers, EITs out there. This is a 115 kV line. That's a line to line quantity by convention. So 115,000 divided by root 3, square root of 3, 1.73 gives us about 66 kV line to neutral. And then remember the 67 volt tap is 1,000 PT ratio. So we divide that by 1,000 and we get 66.5, or you can round up to 67 volts on the secondary. So that kind of gives you a gut check that we picked the right ratio with the right tap. Any questions on PTs? Let me check the chat, see if anything, number of windings, 1001, good job. I've seen single pole breakers to protect the PT circuits. Yes, good point, Hamad. You're thinking like a molded case circuit breaker. Instead of a fuse, you can also use that kind of like your home AC panel circuit breakers, something along those lines instead of a fuse. That is also a possibility nowadays. Good point. Any questions on CTs or PTs before I move on to my next topic with the rest of our time? We are closing in on the end of our first session pretty quick here.
Hey, Josh, question on PT ratios. So I've seen a lot where the secondary voltages or primary voltages that I'll display on the nameplate are really taken as what it's rated at, not so much what it's actually going to give you. So how do you tell the difference of what the actual PT ratio? Because you can get like, a ratio that might be 980 something to 1, and you just go ahead and pick it at 1,000 to 1.
Yes, so you have a nameplate ratio, but then the reality is that the nameplate primary voltage may or may not exactly match your system's nominal operating voltage. And keep in mind that your system's always voltage up and down, plus or minus 5% as well. So you do need to take the nameplate ratio. It may not be exactly 67 volts. Say this was the same PT, but it was a 100 kV line instead of a 115 kV. I don't know if that's realistic, but let's just use it for hypothetical sake, right? In that case, if you had a 100 kV line divided by root 3, and that's 58K line to neutral, you're still going to have that 1,000 to 1 ratio. That's a fixed physical quantity of that PT. So divide by 1,000, the smaller tap would be, you would expect to see somewhere close to 58 volts on the smaller secondary tap for a 100 kV system, even though it's 115 kV PT. Did that kind of clear up your point there, Sean?
Yeah, I think that's good. Thank you.
Great question. You are correct. I've seen that sort of situation before. Let's go into probably our last topic we have time for today, and then we'll pick it up with additional tomorrow. And that's test switches. I mentioned earlier that, in these CT circuits and these PT circuits, we're not drawing them on here yet in our one-line diagrams. Test switches usually don't show up on a one-line diagram. It's too much detail. You can't squeeze everything in there. You need to kind of pick the most important stuff to put on the one line. It's more of a high-level summary. We'll talk more about that tomorrow. But test switches are very oftentimes used with our protective relays. In fact, some of those pictures I showed you earlier of the relay panel lineups here, you see under each relay, there's a set of test switches, or one or more test switches in some cases. Sometimes you have 3 sets, 10, 10, and 10, so that's 30 test switches. Sometimes you can order it with 20 or with just 10, whatever your needs are for that relay's application. But what is a test switch? I think I can squeeze this into our last 10 minutes together. The best way I can describe it for you is ABB demonstration here. Flexi test configurator is what I usually type into my Google. FT switches. And this is actually a test switch block. And so it has 10 different switches that you can configure on here, labeled alphabetically A through J. And for starters, I'm going to make them all current test switches. Shorting current test switches. But then I'm going to change the last 4 of them to potentials instead of currents. Let's see here. P, there we go. That's what I wanted to see. P and P, but P is for potential. C is for current, but the C is for a shorting current test switch. And then a lot of times I'll see clients that will ask to have their CTs in red and their PTs in black or some other color convention, maybe vice versa. There are different companies with different standards of what they'd like their color scheme to be on their test switches. But this is a common thing I've seen, shorting current test switches in red handles, single pole, potential test switches and black handles. In fact, I think I showed you an image of that earlier, right here. This is exactly that test switch, currents and potentials. So what is this doing? Why is this here? We call it a test switch. It's obviously there for some purpose in the testing of these relays. And what we're trying to do here is a means to isolate the real life primary power system equipment, the PTs and the CTs, from the back of the relay, and then allow us to inject or simulate some test signals into our relay for our relay test plan to be executed. The best way I can probably show you that is a friendly commissioning trip I had last year. I'm sitting out there with an Omicron test set right here, and controlling that Omicron test set with my laptop on the Omicron software. And then from the test set, I wired into these voltage and current signals into this test paddle, which you open all those test switches and you squeeze in this test paddle. And all of a sudden, when you open those switches, you've isolated the actual real life CTs and PTs from the back of the relay. The convention is that the top of the test switch, the odd number terminals, are wired to the back of the relay to your IA, IB, IC, in and out, polarity dot and non-polarity dot signals. The 13 through 19 here would be wired to VA, VB, VC, and then you jumper them together on the back of the relay and bring back a VN, a neutral voltage. And what you do here with the currents, we talked about how it's very dangerous to have an open circuited current CT secondary wiring. So these are shorting test switches. If you open the A, or you open the B, or you open A and B, it actually short circuits the field side. I should specify that up here, this odd number terminals is typically wired to the back of the relay. The even number terminals on the bottom is typically wired to the field equipment, to the actual PTs and CTs, and your bushing CTs, your bus PTs, et cetera. And so when you open your current shorting test switches, it shorts 2 to 4. You open C and D, it shorts 6 to 8. Actually, it's a make before break. So as soon as you start to open A, it shorts these before it even opens it to avoid there from ever being an open circuit condition on your CT secondary. And then you'd have VA, VB, VC, and VN on your potentials here. So you inject, simulate overcurrent condition with your test set, for example. And like I was showing you over here, you'd be, these wires are carrying simulated voltages and currents, not real life power system voltages and currents. You can also wire a trip signal out of your relay back to the test set to confirm that it issued a trip properly when it should have, to confirm what the time was that that trip was issued in, that it was expecting based on maybe an overcurrent, inverse time overcurrent curve, et cetera. Maybe a distance relay time delayed element, zone 2, et cetera. We've talked about these concepts in previous courses. That's not what we're after in this course, but that's kind of the intent of a test switch. But you can also use test switches not just for voltage and current PT/CT inputs. You can also use test switches to isolate DC inputs and outputs. And we haven't really gotten to the DC side of things yet. That will come later as we're looking at DC schematics. But I want you to be aware that you could, for example, use a test switch to wire the breaker auxiliary status contact, a 52A or a 52B that's coming into your relay. You can use a test switch to isolate that true power system from the back of your relay. Some people will use one test switch for an input, some will use two. Some want to just provide a way to isolate the signal. Some want to have a isolation of both positive and negative DC. We'll look more at that in the DC context. But I want you to be aware that, like the trip signal going out, that's another great example of a DC signal you would want to have on a test switch. So you can open it up so that as you're testing your relay, you don't accidentally send a real trip signal out to your real breaker to isolate a primary system if it's still left in service during that testing. Hopefully you have a primary and backup relay. You still have protection on that circuit during that situation. So that's kind of the intent of a test switch. One other picture that might help shine a little light on that. ABB FT1 test switch. This is a little different configuration, but you see your CTs are wired to the even, CTs and PTs wired to the even side, the field side, and then the odd side is wired to the back of your relay, your voltage and current terminals, current in and current out, polarity dot and non-polarity dot. And then notice that the neutrals are tied together or jumpered on the field side of your test switch rather than on the back of your relay. Otherwise, you wouldn't get 3 returns. You'd only get 1 common return, right? You got to do that in order for this shorting test switch to work properly. Those are just a couple of things I'm pointing out to you on the concept of a test switch. We'll look at those a little more in some real life 3-line diagrams tomorrow.
Joshua.
I see some questions. Yes, Hamad.
So if you're supposed to open, let's say one of the phase A, let's say I can open up the 10-9 test switch block, and then the 7-8.
Mm-hmm.
How would you define the step?
Yes, you would open. This is a little different than the one I configured earlier. It looks like this has currents in the middle. But if A was D and E fingers, you would open up D and then you'd open up E. And at that point, A phase has been isolated from the back of your relay from the real power system. Typically, you wouldn't do just one phase, but I guess maybe in a SCADA checkout situation, you might, I don't know, you'd probably just inject them from your test set. You would probably typically open all of them fairly quickly. I don't know if I'm answering your question there.
Yeah, so let's say if I open up the E10-9 and if I don't open up the D part, it still has shorted the A phase.
Yes, Exactly. If you open one or the other or both, they are going to be shorted properly. So as soon as you open, because you can't guarantee that you're going to truly open both simultaneously at the exact same moment. So as soon as you open one of them, or even in the process of it opening, it's going to short before it's fully open. It's a make before break test switch. Good point.
Thanks.
Let me see if I can catch some of these other questions before we conclude today. If there are any conductor differences required for PT and CT circuits. Yes, I typically see higher gauge on the CT circuits because the amount of current flow you see in a PT secondary is fairly low. And so I think I told you, what did I say, about 10 gauge is pretty common for CT secondary circuit. I'd say 12 gauge is maybe somewhat common on a PT secondary circuit. Remember, with American wire gauge, it's the opposite direction. As the number goes up, the conductor is getting smaller. Can you show one example hand drawing showing CT connected to the test switch? Yes, I will do that in just a moment. Let me see if there's any others I can address quickly. Omicron is favorite test kit. I'm glad you have some experience with that. Opening just one current looks like you've already could possibly cause a false ground trip. So yeah, it's not good practice to open just one, but you're going to try to open them both fairly quickly to one another. What's the purpose of a single ground in the CT secondary circuit? Good question there. If you have multiple grounds, what actually could happen is you could have fault circulating ground currents through your substation ground grid. And so that's why you want only one and only one ground point on each CT secondary circuit. Looks like Sean jumped in there. Great job. So I think this is the last question I'm going to handle for today. And if you have follow-up questions, we can address those at the start of tomorrow. But Hamad asked a great question to kind of show a sketch of a CT input with a shorting terminal block, shorting test switch we're talking about here so far. Let's draw our relay over here. In this case, I'm going to draw it a little more like we commonly do for a single phase. See if I can sketch this somewhat reasonably. This is going to be a test switch on either side of the relay. You know, we'd have our neutral that goes back around. I should have made that green perhaps, but the point is we've got this current terminal here. And then the key thing that you're looking for is that there's this other shorting block here that kind of goes around and bypasses the current input so that when those test switches are in the open position, it is going around the relay input, leaving it isolated, de-energized, so that there's no current flow through the relay. But on the CT secondary, still connected to the possibly still energized primary, you can have current flowing around this relay terminal and back to the neutral just fine, even though the relay is showing no current at that point. So hopefully that gives you a good feel for kind of the general premise. You're going to look at that again on a real life, actual, a little prettier CAD drawing, 1-line, 3-line rendition tomorrow, and you get to see that again. But this is the essence of what we're after. So I'm going to jump to a few concluding notes and kind of call it a conclusion for our first day. If there's been any questions beyond what you've asked today in the live session, I encourage you to ask those questions still. Don't leave yourself with any doubts on what we've covered. We're going to take, this session is recorded. I'm going to upload that recording to my website this afternoon, and I'll send you out an email when it is ready. And you will be able to click the link and go to that day's session on my website. And you're going to have one small homework assignment that I want each of you to complete later this afternoon or this evening or whenever you watch the recording following that. And that homework assignment is that I want you to write a very brief summary of your key lessons learned your key takeaways. What was your aha moments, your epiphanies? You're like, wow, that really stuck out to me. I need to make sure I remember that. You know, the process of you actually writing it out, looking back through your notes and reiterating it helps to solidify it for yourself as you share it with me as your teacher. It helps me to see what you're learning and what you're finding helpful, but it also allows you to see what your fellow students are learning as well. And it's also a proof of participation in this virtual training environment. You must complete all 4 days homeworks to qualify for the certificate of completion at the end of this course. And you also, another great reason to do the homeworks each day is there'll be a free prize giveaway on the final day, day 4, for somebody that does all 4 homeworks. One person will win a free career coaching call, a one-on-one private coaching mentoring opportunity for an hour with me about your P&C career path and goals and aspirations. So make sure everybody does the homework. I really encourage you to do that. It's not required, but if you want that certificate for your PE, PDHs, or just to upload to your LinkedIn profile, strengthen your resume, your CV, do your homeworks. So I hope that you've enjoyed this day 1 of the P&C Design Challenge. I trust you're already kind of learning and growing and taking away some nuggets of wisdom from this first session. And we're going to keep going deeper in subsequent 3 days together on this P&C design realm. So this is a challenge. I challenge you to make every effort to attend the live sessions, engage in the homework and the Q&A opportunities, et cetera. So what I was saying earlier, if you have any more follow-up questions as you do your homework, as you summarize your key lessons learned, feel free to also ask any additional follow-up questions as part of that homework. And I'll either type you back a response this evening, tomorrow morning, or we'll address it in tomorrow's session. So we'll reconvene again tomorrow at noon Eastern Standard Time for day 2 of the P&C Design Challenge. Hope you all enjoyed it. See you again tomorrow when we resume. Take care, everyone.